This is a video, but I promise I am here. This seemed the safest option as it's evening on bonfire night here. I've got a dog and lots of fireworks means the potential for disruption is pretty high. I'm Alex Rowlands and I'm from the Diabetes Research Centre at the University of Leicester. I'm teaming up with Jonah Thomas, also from the Diabetes Research at Leicester, and we're going to discuss the methods conundrum that we all face when assessing physical behaviours using wearable devices. As Charlotte has outlined, there's a lot of variability in the methods used to collect and or analyse accelerometer data. In an ideal world, we'd like to be able to get from this heterogeneity to being able to harmonise data across studies. And some of the key sources of variability are the measurement device that's used, where the device is worn, the methods applied for processing and or analysing the accelerometer data, and the physical behaviour outcomes that we choose to generate. So from all these sources of variability, we'd like to get to a point where we can harmonise and or compare the physical behaviour outcomes from the different studies. And there are a number of steps that need to be taken to ascertain how best to do this. So Grace has talked about the need for reference standards, and Marco about the need for quality performance evaluation. And Jonah and I are going to talk about establishing the potential for harmonisation between different methods. So specifically, I'll talk about a data set that could be used as a resource to inform the potential for harmonisation. And then Jonah will discuss a research question that uses this resource. For this data set, the AMBER measurement group at Leicester collected data from concurrent wear of devices at several wear sites. Now, all of the devices were worn 24 hours a day for 3 days. And data collection is currently ongoing, but we aim to have a total of 40 to 50 participants. In these types of studies, it's always a balance between the number of devices and the number of wear sites you'd ideally like to include, compared to what is actually going to be realistic and feasible for the participants, given that they need to wear these monitors for 24 hours a day. So our approach to this was to select one device to be consistent across all wear sites, and then to add other devices at the wear sites where that particular device is most commonly worn. And we also wanted to make sure that we included the main wear sites used across studies in the past, present, and future. So the device we selected to be worn across all wear sites was the Genie Active. Part of the reason for this was existing studies have found that the outcomes from the Genie Active can be considered equivalent to those from the Activity as long as the data are processed consistently. The wear sites we included were both wrists, the waist, the thigh, the upper arm. This one's less common, although it is sometimes used, particularly where health professionals are included, as they often can't wear monitors on the forearm or on the wrist. We added the Fitbit as it's perhaps the most widely used consumer device, and we put this on the non-dominant wrist as this is the manufacturer's recommended wear site. We also added the Actigraph on the waist as it's commonly used there, and the ActivePal on the thigh, again, very widely used. In a subsample of 10 to 15 participants, we used 2 sleep devices for one night. We used the Z Machine Insight, which is an EEG-based sleep monitoring system that uses adhesive stickers behind the ears, is validated against PSG, and is feasible for home use on multiple nights. We also use the MFit, which is an under-mattress sensor for monitoring sleep. So this isn't a wearable, might be known as a nearable. The resulting data set will be made available for other research groups who wish to investigate the comparability of data outcomes between devices, wear sites, processing analysis methods, and so on. Hence, we want this data set to be a resource for other people to use. An example research question that can be addressed using these data relates to the recent meta-analysis published in July on step counts and health by Ding and colleagues. As you'll know, this study had a lot of media attention, which focused mainly on the conclusions that 7,000 steps per day was associated with clinically meaningful improvements in health outcomes, and also that 7,000 steps might be a more realistic and achievable target for some people than the widely known 10,000 steps per day target. However, what didn't get widely reported is that the authors highlighted that most of the data they included in their review were from research-grade devices which were worn for several days, and that this might not align with step counts from consumer wearables. The authors went on to stress that translating the proposed quantitative step counts, so that's 7,000 from this study, target to the real world might require additional research and consideration. So this begs the question, what does 7,000 steps look like on different devices, different wear sites, and or with different processing methods applied? This becomes a crucial question if recommending these step targets to the public who will likely be using their own devices to assess their steps. So I'm going to hand over to Jonah to explore this.
Thanks, Alex, for that great introduction. Right slide. There we are. So as Alex mentioned, I'm going to talk through our comparison of step counts between research grade and commercial wearables. My name's Jonah Thomas. I'm a research associate and data scientist at the University of Leicester, and I work out of the Leicester Diabetes Centre. So as Alex mentioned, this Lancet review found that 7,000 steps is associated with all-cause mortality and a range of other health outcomes. But when we look at the 14 studies they included in their dose-response meta-analysis, which produced this recommendation, 13 of these 14 were worn on the hip, and 8 of these were actigraph, and only 1 was worn on the wrist. As we know, the wrist is a commonly used wear site and is being increasingly used in current studies. And the World Health Organization said yesterday that they're favouring the wrist as the location for national surveillance. So it looks like the wrist is going to become predominant in years to come. However, a lot of our evidence base at the minute still comes from hip-worn accelerometry. And therefore, we need to see how this compares to consumer devices, which are commonly worn on the wrist, such as the Fitbit, Apple Watch, or Garmin, for example. So this was our main sort of question. How do steps measured by other devices at different wear sites and using different combinations of algorithms compare against steps measured using the actigraph at the waist? So our aim was to investigate how step counts compare between outcomes generated across research-grade devices and algorithms and consumer devices, and specifically, what does 7,000 steps from the actigraph look like across the other devices? And then the flip of this is to see what does 7,000 steps from the Fitbit look like on these other devices. So just some naming clarification as we go through this presentation. So when you see the word actigraph on the following slides, we're talking about the actigraph device, which was worn on the hip, and the step count was generated using the ActiLife algorithm. When you see Fitbit, we wore the Fitbit Charge 4 on the non-dominant wrist, and the steps were generated by the Fitbit proprietary algorithm. When you see GenieActive Oxford, we're talking about the GenieActive device worn on the non-dominant wrist, processed using the Oxford algorithm. When you see GenieActive VeriSense, this was a GenieActive on the non-dominant wrist, processed via the VeriSense algorithm. And when you see ActivePal, this was the ActivePal worn on the thigh, processed using the Kriya algorithm. We are going to use the Processing PAL software in future to look at this, but for the minute, we've used the PAL technologies and the Kriya algorithm. A 10-hour minimum wear criteria was applied to all days based on previous actigraph studies. So looking at our wear time and average steps, when we look at all of this data across all our participants, 86 days in total met our wear criteria across all 5 of these devices. When we look at the mean steps, we can see the mean steps is lowest in the actigraph at just over 8,500, followed by the ActivePal at around 9,000. The GenieActive using the Oxford and the VeriSense algorithm gave similar estimates, around 10,000 on the Oxford and around 10,500 for the VeriSense. And the Fitbit gave our highest estimate of steps at around 11,000. When we look at our standard deviations, we can see our actigraph had the smallest standard deviation and our Fitbit had the largest. Digging into this data a little bit more by looking at the medians and the interquartile ranges, we can see again the median for our actigraph was lowest, and we can see that our interquartile range was probably the tightest in this group. When we look across the other devices, we can see the medians are relatively comparable, with the Fitbit slightly above and the ActivePal slightly below, but the interquartile ranges are similar across all these devices, suggesting a similar spread of the data. When we look at our step count distributions, this is a density plot showing the different devices by color. We can see this red line that I've highlighted is the actigraph, and we can see this is peaking around the 7,000 steps per day. This gold line here that I've highlighted is the Fitbit, but I think the key takeaway here is that the Fitbit, the GenieActive using the Oxford algorithm, the GenieActive using the VeriSense algorithm, and the ActivePal all have very similar distributions, and there's not a lot we can find that differs between these. It's just the actigraph that stands out as being slightly more skewed to the left than the other devices. Looking at the interclass correlations between the devices, this top graph is this top table is a comparison of the actigraph to all our other devices. So we can see our lowest interclass correlation is between the actigraph and the Fitbit. We see our highest interclass correlation between the active PAL and the Genie Active using the Oxford, both above 0.9, which would suggest excellent agreement. And the Genie Active VeriSense is slightly lower at 0.72. Our second table on this slide is looking at the Fitbit compared to the other devices. We can see, again, the Fitbit compared to the actigraph is 0.65. Our active PAL is lower here at 0.62, and our Genie Actives are both 0.71 and 0.76. So we can see, again, there's less agreement between our Fitbit and our other research grade devices compared to the actigraph and our other research devices. These are Bland-Outman plots. So this first slide is looking at our actigraph versus each of our other 4 devices. So we can see our mean bias is highest with the Fitbit at an overestimation of 2,380 steps. We can see that our Genie Active Oxford has a mean bias of 1,400 steps, and our Genie Active VeriSense is slightly higher at 1,851 steps. And we can see compared to the active PAL, actually there's very good agreement when we look at the mean bias is only 350 steps overestimation on average. When we look at our 95% confidence intervals, we can see that the widest confidence intervals are for the comparison of the actigraph to the Fitbit, followed by the Genie Active VeriSense algorithm, and actually our agreement for the Genie Active Oxford algorithm and our active PAL comparison. The 95% confidence intervals are really quite tight, with only a few outliers towards the bottom of the actigraph active PAL Bland outcome. This slide is comparing the Fitbit with our other devices. So we can see this is the same as before, just flipped. So we've now got the underestimation compared when we compare the Fitbit and the actigraph of minus 2,300 steps. We can see that our Fitbit compared to our Genie Active Oxford and our Fitbit compared to our Genie Active VeriSense actually has relatively low mean bias at under 1,000 steps for each. And our Fitbit compared to our active PAL has a higher mean bias at an underestimation of 2,000 steps. But we can see here that our confidence intervals are wide for all of these comparisons and wider than we saw with the actigraph device. So to try and answer the question of what does 7,000 steps on the actigraph look like on the other devices, we applied standardized major axis regression analysis. This type of regression analysis allows there to be error in the measurement on both the X and the Y axis. So it acknowledges the fact that both the actigraph and the Fitbit device are not a true gold standard measure of steps, and there's likely to be some error in both devices compared to the person's true step count. So when we use this approach, we can see that 7,000 actigraph steps correlates actually to around 9,000 Fitbit steps. And this model had a relatively good R squared value, so it had quite a good fit of 0.62. When we look at the Genie Active Oxford, we can see that 7,000 actigraph steps actually correlates to about 8,000 Genie Active Oxford algorithm steps with a very high R squared of 0.92. When we look at the VeriSense, we have a slightly lower goodness of fit, but 7,000 actigraph steps is around 8,700 Genie Active VeriSense steps. And with the active PAL, we're very close to that mark. So 7,000 actigraph steps equals around 7,100 steps on the active PAL, again, with a good model fit. Flipping this over again, so what does 7,000 steps on the Fitbit look like on the other devices? We can see that 7,000 Fitbit measured steps actually equals 5,400 steps on the actigraph, so significantly lower. And we have our model fit of 0.62 again. When we look at the Genie Active Oxford, we can see that there's actually less steps compared to the Fitbit, but our model fit is lower here at 0.53. The Genie Active VeriSense is very comparable and seems quite similar to the Fitbit, just over 7,000 steps. And our active PAL again is significantly lower at 5,302 steps. It's worth noting that all of the model fits when we're comparing with the Fitbit devices are lower than when we're looking at our actigraph devices compared to our other devices. So what are some of the implications and conclusions we can draw from this? So as with when we're looking at MVPA metrics, interpretation of step count data needs to consider the device, the wear location, and the algorithm, as these can all affect the step estimate that is derived. Data sets which have used multiple devices, such as the Leicester comparability study, that have worn devices across multiple wear locations, provide a resource for investigating comparability and or the potential for harmonization of outputs across devices. If 7,000 steps measured on the actigraph are recommended, someone measuring steps with the Fitbit may only be performing 5,500 steps, but think they're meeting the 7,000 step guideline. I'd like to thank you all for listening. I'd like to thank the Amber team, Shelley, Henrik and Israel, and Alex and Charlotte as well, and also all the study participants that took part in this research.